So now hopefully you have an understanding of dealing with just series circuits, the resistors that are in series and just resistors that are in parallel. The diagram you see on the board on the screen right now is what we call a complex circuit or a combination circuit. The process is going to be the same, and you see I've kind of created a couple of tables already. That's also to save some room here because these problems can get a little long. They're not mathematically difficult. They're just a little tedious and you got to kind of stay organized. And normally I have whiteboard and everything else. And here I can't switch screens without losing my writing. But the circuit you see on the left-hand side, you have four resistors. You have a EMF, a voltage source of 24 volts. Okay. Before you just may have seen, say, R1 and R2. But now I have, in essence, a combination circuit where we'll call this R12 branch and R34. Those, okay, R1 and R2 are in parallel because I got an option. I get to this breaking point and I have an option either to go to this way or I can go here. Okay, I don't have to go through both. Now I have to go through one of these. So R1, R2 here, R12, R34 are in series. So I can't just treat them just as parallel or just as series. The general rule for these is relatively the same. I want to get this down into one circuit. You can see here I called it 1, 2, 3, 4. I know it gets long, but again, it's going to help understand if you've combined circuits or resistors or not. I need to find that equivalent resistance. The first thing you want to think about is get rid of all branches. That's what I want to deal with. Any kind of parallel branch I see, I want to get rid of. Okay. So when I do this, I'm going to redraw it, and I'm going to redraw it every time. I'm going to have a resistor. Okay. This is still going to be my 24 volts. This is now going to be my R12. This is now going to be my R combined 3, 4. Now remember, in parallel, you have 1 over R12 would be 1 over 100 plus 1 over 250. That's how I'm getting the 71.4 you see over here in this table. R34 would be 1 over R34 plus equals 1 over 350. Plus 1 over 200. And that's how I get my 127.3. Okay. Now I still have combinations. Now, if you look at this, and I just gave you this, those two resistors are in what? Series. So I can combine those into one equivalent resistance. Now in series, they just add up. So I'm just going to add up the 71.4. So this is going to be my equivalent resistance, but I like to write it like this. Still 24 volts. And when I add them up, I get 198.7. Okay. Now I know that the EMF here is the voltage, okay, 24 volts. Now I know V and I know R. So what can I do? I can use V equals IR to find out the equivalent, in this case, resistance or current. Sorry. So you'd have 24 I times the 198.7. Okay. And you'd find out that that's 0.12 amps. Now you just start applying your rules back. Okay. So when I look back at this circuit, and you just keep working your way back, these two are in series. What is the same in series? Current. So I know that I12 is going to be 0.12 amps, and I know I34 is going to be 0.12 amps. Okay. Now, you have R and you have I. You can find V. So all I'm going to do each time is apply V equals IR. Okay, so you'd have 0.12 times 71.4, and I'd have 0.12 times the 127.3. Sorry, running out of space here. So for V12, voltage drop across 1, 2 would be 8.6 volts. The voltage drop across 3, 4 would be 15.3. So now I got to break it down because I'm still, and that tells me when I write it this way, because I have two subscripts, I know I'm not all the way done. So I work my way back. All right, so R1 and 2 are in parallel. Well, what's the same in parallel? Voltage. Okay, so V12 is going to be V1 and V2. That's going to be 8.6 volts. That's going to be 8.6 volts. Okay, V3 and 4 are in parallel with each other. So they're both going to have a drop of 15.3. So we're just applying our rules from last lesson. Okay, well, now you got two of the three. So just apply Ohm's law. So for instance, for the first one, I'll just show you the first one, 8.6 V equals I times R. Okay, and they're going to get relatively small numbers. So I1, you're going to get 0.86 amps, 0.086 amps. Okay, for I2, again, just doing it same way with the different numbers there, 0.034 amps. I3 would be 0.043 amps. And I4 would be 0.077 amps. And so I just work my way down all the way back. Just applying. It's really nothing more than really just a puzzle. Okay. So there's a combination, an example of a combination complex circuit. All right, let's do one more and with a slightly different twist to it. All right. I've already redrawn these. Again, part of the reason is to save space, but I'll explain why I did and how I did it using a diagram, a circuit diagramming tool. Most of it's just to save space here, and you can see I have my tables already set up. But again, I'm gonna walk you through it all. All right, so the first circuit you see up there, a whole mess of stuff. Okay, whole mess of things up here. Now, automatically I see this branch here. Okay, this parallel circuit. That's the first thing I note. I want to get rid of it. Okay, I want to get rid of it. So what I'm going to do is try to combine those, but I can't just combine those because this R3 and R4 are in series. So if you look at this next step, what I did was go ahead and just combine those. They're in series. So you add up, okay? You're going to add up their resistances. 2 plus 6 is 8. So that's how I get this combination right here. Okay? Now I can get rid of the parallel branch. Again, that's 1 over. So the 1 over the equivalent is going to be 1 over R34 plus 1 over R5 there. Okay, and that's how you get the R345 to be 2.67. So now that you've gotten rid of that branch, if I just gave you this, you'd be pretty happy because you have 1, 2, 3, 4 that are just in series. And in series, what happens? You just add them up. So just add up all the resistances and you should get 12.67 ohms. And I'm down to this equivalent equivalent circuit. So now you just start undoing everything. Okay. So you have the EMF. Okay. It's a 9-volt battery. You can easily find the equivalent current just using V equals IR. And that's all you really use for every problem. So the equivalent would be, so your equivalent would be 0.71 amps. Okay. So now I just start working my way backwards till I get to the original. Now I have them in series. What's equivalent in series? Current. So all these are in series. So that's 0.71 amps. That's 0.71 amps. That's 0.71 amps. Sorry. And that one's 0.71 amps. Okay. Now, Now that I see this, I know I have 1, 2, and 6 down to the actual resistor that it is. And I can tell right now the 3, 4, 5, I'm going to have to break apart. That's why I like doing this notation the way I do it with the subscripts. Now you have two of the missing pieces. You can find the third just applying Ohm's law each time. So for instance, R1 would be, whoops, V1, I would be 0.71 times the 3 ohm resistance, and you'd get 2.13 volts. And again, just applying Ohm's law each time. So 6 times 0.71, you'll get 4.26 volts. 0.71 times 2.67, you'll get 1.9 volts. And 1 times 0.71 is you get 0.71 volts. All right, now these are single down to the singles. I don't have to break these down. So I'm actually going to go back up here and fill out this original chart. 2.13 volts, 2.13 volts. This would be 0.71, 0.71. 2 is done, so 4.26, 4.26, 0.71, 0.71. 5 is not done, 6 is done. Okay, so this will be 0.71. This is 0.71. All right, so now I'm here. Okay, so now I'm going to break it down. So I'm moving to the next level. These two are in parallel, 3, 4, and 5. Well, what is the same in parallel? Voltage. Okay, well, that equivalent resistor was this one right here, and the voltage was 1.9. Okay, so 1.9 would drop across the top, and 1.9 would be deposited across the bottom. Again, think of your toll booths. You're going to pay the same rate no matter what lane you're in. All right, so to find the current, then you're just going to use Ohm's law. So 3, 4, I 3, 4, resistance 3, 4. Okay. So 8, I 3, 4 times that equivalent resistance. Oops, that was 1.9, sorry. This is 8. And your current through that would be 0.24 amps. And you'd use the same equation, just different numbers. You now have a resistance of 4, voltage of 1.9. Solve for the current, you'd get 0.4 amps. And I know 5 is done because there's no other subscripts. So 1.9 volts and 0.48. Okay, 3, 4 still has 2 subscripts, so I got to break it down apart, another part. 3, 4 in series. What's the same in series? Current. So if I'm looking at this equivalence resistor, 3, 4, the current is 0.24. So that tells me 0.24 is going to go through this one, and 0.24 is going to go through that one because they are in series. So you have current and you have resistance. So for instance, for 3, current would be 0.24. The resistance would be 6. And you'll find out the voltage drop would be 1.44 volts here. And for R4, you're going to use 2 as your resistance, 0.24 as your amps. And you should find 0.48 amps. Or volts, sorry, 0.48 volts. It looks like it's just applying your series and your parallel rules. Get rid of your branches first, and then just apply your rules and work your way back. I really like setting up these charts ahead of time Every time I redraw the circuit, set it up, and it just keeps you a lot more organized. Okay. Again, if you have questions, make sure you email me. Give you some. You're going to be doing some practice problems with this as well as lab simulation. Um, this is as complicated as the one that I'm probably going to give you or expected for you to do on an assessment. Um, again, please email me. Pay attention to the Zoom meetings that will be thrown out at you. If you need the help, join in with me, ask me the questions, let me help you and work, our way through it virtually at this point in time. Okay.